Joe Hellerstein, here to tell us a bit about cloud programming.
Thanks very much, and thanks for having me. I'm excited to be here virtually from California. So today I'm going to talk about cloud programming, this notion called Calm, and sort of new programming model we're describing as PACT programming. It's a talk in 4 parts. We'll start by talking actually about serverless computing, and then I'll introduce the idea of avoiding coordination and why it's so critical to distributed programming. Then we'll cover the Calm theorem very quickly and conclude with the Hydro project and PACT programming. So there's a saying in computer science, as we look at the history of computing, that for every new platform, a programming model arises that unlocks the potential of that platform for a generation of programmers to do new and unexpected things. And this tradition goes back to mini computers, Unix, and C, and the Turing Awards that were given to Ritchie and Thompson for that work. Move from mainframes to what we think of as modern computing wouldn't have been possible, not only without this cheaper hardware, but also without that change of programming model that was suited to that hardware. And arguably, there have been similar sort of programming model innovations for supercomputers, for visual programming on personal computers, and for smartphones. And of course, the most recent platform that we've been facing is the cloud. And you might ask, well, what's the programming platform or programming environment that's native to the cloud? And the answer to this is we don't have a real concrete answer to this yet. There isn't a good model of this is the right way to do cloud programming. So to me, this is a big question. How will folks program the cloud? And when I say folks, I don't mean infrastructure engineers at Microsoft and Amazon. I mean regular programmers who have ideas that they want to turn into reality. So how will folks program the cloud in ways that foster unexpected innovation? And perhaps the reason this is taking so long is that the cloud is really very different from the other platforms we've had in the past. Distributed programming is hard. It entails all the problems of parallel computing, distributed consistency, partial failure of components. And increasingly, the way we want to write cloud programs is that they should auto-scale up and down, so you're getting cost-effective use of compute during periods of low and high utilization. Auto-scaling makes this even harder because you have to write programs now that are elastic. And so these are really, really hard programming problems. Now, I've been working on this for a good decade, and this goes back to our work on a language called Bloom that we were working on in the earlier part of the last decade, and that we delivered into practice, and that you can still play with if you like. And I guess my point here is that there's not just our group, but others have been working on this problem of distributed programming for a good decade. Now, a couple of years back, serverless computing arose as a possible way for developers to be able to start writing their own code and deploying it at scale in the cloud. And this was really exciting because it was, for us at least, who'd been doing the research for a long time, evidence that the cloud vendors were taking notice of this problem. Instead of just building replicas of on-premises technologies and selling them, they were opening up the cloud to programmers. And that was really great. But as we started to look at these offerings, things like Amazon Lambda, Google Cloud Functions, and so on, what we found was that they were pretty restrictive. And so we wrote a paper a couple of years ago, which got quite a bit of controversy going, where we were really pretty critical of these systems. And we pointed out that they're really, really bad if your application needs to access data in a latency sensitive way. And also that they don't allow programmers to send inbound network messages between cloud functions, which means that you can't really write distributed algorithms in serverless computing. In some sense, they don't allow you to use the cloud for the power that it offers. You can't harness multiple machines working together, and you can't get efficient access to data. Those are sort of the two signature things about the cloud that we'd like. So we started out by critiquing, but we went forward and were constructive. We didn't simply say, things are bad. We presented a couple of years of research in the RISE lab at Berkeley showing what would be possible that could overcome these hurdles. So this was systems that really worked that we did at Berkeley. The ANA auto-scaling multi-tier key value store, which I'll talk about a little bit later. And then we built our own stateful functions as a service system to show that you could really do these things in a functions as a service framework work if you thought about it hard. So we had a series of academic papers on these systems, and they offered disaggregation of compute and storage, which is an important feature of serverless computing, but and they also offered the auto-scaling features that we want in a serverless setting. But they also offered low latency I/O, networking between cloud functions, consistent handling of data, isolation, and fault tolerance, all the kinds of things we'd like to get out of a computing environment. So I'll talk just briefly about some of these later. Really, the thing is that serverless computing, it really doesn't take us that far anyway. Serverless computing is just a bunch of sequential user-defined functions hosted in the cloud. That's not really a programming model. That really doesn't help us that much in harnessing the cloud to write interesting distributed programs. And so I guess, in the spirit of the matrix, what if I told you that the work we're doing is really just the beginning of what's possible in distributed and cloud programming? So that's what I'm going to hint at today and tell you a little bit about what we think is possible and what we're doing about it. So I think it really is time in the computing community for us to tackle this big question of how will we program the cloud? The time has come, and serverless computing was sort of a hint that there's a pent-up hunger to do this. So having talked a bit about serverless computing, let me talk about one of the hardest things in distributed programming, which is avoiding coordination. So the first step in really empowering programmers to write distributed programs is to allow their code to manage state, which is to say data. So state is not, in fact, a state like California where I am here. What I really mean by this is the local data that's managed by code across invocations. So think of this as state in a file system, state in a database, or even state in global variables in a distributed program. Okay, or even state in local variables for that matter. So how do we move this state around? How do we manage it? How do we make sure it's correct? These are the things that get super tricky in distributed programming. And there are kind of two aspects of this problem. The first is that this data is kind of heavy and it's expensive to move it around. People sometimes talk about this as data gravity. And to be frank, this is a policy problem, a performance problem. We in computer science are really good at tuning for performance. Developers are awesome at this. It's something you can iteratively improve by deploying and measuring and getting better and better. So I would argue that this is a policy problem and it's not that hard. And in most applications, it ends up getting solved unless there's an architectural reason it can't be solved. Okay. The second challenge is the one where things are really difficult. And it's sometimes the reason that people put up architectural boundaries to data movement, which is distributed consistency of data is very tricky. This is a correctness problem. It has to do with the computer doing what the programmer will expect. It's difficult and it's simply unavoidable if you're going to have stateful computing in a distributed environment. So let me talk about this a bit. The challenge, and some of you may be very or intimately familiar with this and some of you less so, the challenge is to keep things consistent across distributed computers. So in essence, for consistency, we want two agents that are far apart from each other to agree or to ensure that they will eventually agree on some common knowledge. So here in the picture, right, we have these two lovebirds. They currently are separated. One's in the daytime, one's in the nighttime because they're far away, but they agree that X is love. They are in love. Life is good, and they agree on that. So this is a classic example of data replication. This fact, X, has been replicated in these two different places, and currently they both have the same value for X. But how do we know if they're going to agree on this value if they're far apart? Over time, things could change. One of them could change the setting of this variable, right? One of them could decide, you know what? It's not love anymore. It's poop, right? But the actor sort of in the sunshine still thinks it's love. And so now they disagree. When they next communicate or when they come back together, things could only get more confusing, right? Because they may have taken many steps independently based on their assumption about X before they come back together. So that X isn't the only thing they disagree on now. They disagree on many, many things because of the consequences of X, right? So this is a little sort of parable, but this is exactly the kind of thing that happens when you have computers communicating over networks. Okay, this is a classical problem in computer science. This is a picture of Leslie Lamport, who won the Turing Award for his work on distributed computing, including the notion of distributed clocks and the Paxos protocols for agreement. Okay, and the classical mechanisms introduced by people like Lamport or the two-phase commit protocols that come out of databases, these are protocols to coordinate multiple distributed computers so that they can agree and move forward on important state decisions. Okay, so Paxos is one, two-phase commit is another. This is tricky stuff. So every time I teach this to undergrads or graduate students at Berkeley, I need to make sure I go back to the books, especially with Paxos, make sure I've got the details right and I've got it very clear so that I can lay it out for the students so they'll have a hope of understanding it. Unlike many tricky things we learn though, Paxos is not only hard, it's also a pretty bad thing to use. And so this is one of those pieces of technology that's complicated and also undesirable. Let me tell you what I mean by that. And don't take my word for it. This is James Hamilton, who's one of the pioneers of the modern cloud. James famously worked at IBM on databases, at Microsoft on operating systems, and then started working on warehouse scale computing at Microsoft, and was an early member of the AWS team that really built out what is the modern cloud today. And James at a workshop some 13 years ago now had this amazing quote, which I like to read as poetry because I think it's just beautiful. And it goes like this. The first principle of successful scalability is to batter the consistency mechanisms down to a minimum, move them off the critical path, hide them in a rarely visited corner of the system, and then make it as hard as possible for application developers to get permission to use them. The stuff in red is the money quote here, right? What we're saying is that developers simply shouldn't use the techniques that Lamport and others developed. So why is Hamilton saying this? Well, basically, two reasons. One, when you're doing coordination, you're waiting for other computers to make a decision, which means you're not doing useful work. And if one of those computers has high latency, then you're waiting for a very long time. Everybody's waiting for a very long time for the laggard. And it's worse as you scale up because there's more participants and more probability that someone's slow. But it gets worse than that because of queuing effects. So if some junior programmer decides to call the Paxos library, introduces a delay into the system, in large deployments, that delay often cascades to many other services, particularly in a microservices environment, so that it's very hard to track down why all the services in an entire site are suddenly slow. And then, only with some root cause analysis do you realize it was this one program that nobody really cared about that was slow because it was using a coordination protocol it shouldn't have been using. So these are the tales that James was telling in these early days of the cloud and convincing us that really we should avoid coordination at all costs. So the problem is this coordination problem is well studied. I mean, we've known about this in databases and distributed systems forever. And the solutions are these coordination solutions. They're expensive. So how do we work around this? And the path to a solution is to raise the abstraction level into the programming language. So traditional distributed systems and distributed databases are all about reads and writes, I/O, whether they're reads and writes to memory addresses or reads and writes to files or databases. And the question is, maybe we could do better if our programming language actually understood what our program wanted to do, and it could avoid coordination because it understands that the program doesn't necessarily care about every read and write exactly the way that it's been specified. So there's a great Far Side cartoon, and my former student Peter Bayless gets credit for this. It used to be a cartoon, What We Say to Dogs, but we changed it to What We Say to Databases. And so, at the top, he's saying in English, okay, database, be good, and move one iPhone from inventory to Bob's cart. But all the database here is blah, blah, read, blah, blah, write, blah, blah, read, blah, blah, write, right? The database doesn't understand anything that the application knows. It just sees the read and write streams. And there's a lot of information in that application that could let us avoid coordination. So suppose that you understand your program semantics. And this is now like a theory question, so we're going to move to the whiteboard here. Suppose that you really did understand. Suppose you had a programming language where it was easy to really figure out whether you needed coordination. Would that solve our problem? Right, so we asked ourselves this question a while ago. Which programs, assuming we had full knowledge, do have a coordination-free implementation? There's a way to get those programs to run without coordination. Those are the programs you should let your junior developers build, right? And then you should force them not to do it with coordination. But these are the things that it's possible for them to do without coordination. And which programs require coordination? There is simply no way to build the semantics of these programs without calling these expensive subroutines. Those are the programs you'd better put in the hands of senior developers who are in careful coordination with the ops team to get these things deployed. All right. So I want to know what's in the green circle. And what's that green line that separates things that are in the red circle? And this is very much a question of computability. It's the distributed systems version of P versus NP. I want to know what's coordination free and what's not coordination free. And then for programs that are coordination free, I want to find solutions that are implementations of those programs without coordination. Right? Turns out Lamport and everybody had never asked this question. Nobody had ever asked, what is Paxos for? In some, Paxos and those protocols are really supposed to be for the red programs. The green programs shouldn't use them. And no one had figured out, like, what is this boundary between coordination-free programs and the rest of the programs? So that brings us to the Calm theorem. And what the Calm theorem says is that the programs we can build that are coordination-free, the ones in the green circle, those are programs that have a consistent output with a coordination-free distributed implementation. What programs are those? It's exactly the programs that are what's called monotonic. Okay, so the monotonic programs are exactly the programs in the green circle, and that green edge at the edge of the circle is the monotone boundary. Everything non-monotone is red on the outside of the circle, and everything that's monotonic is inside the green circle. All right, and this was a conjecture that I posed at a keynote talk at a ACM Pods conference back in 2010. About a year later, a graduate student in Belgium at the University of Hasselt proved that this was true, and then subsequently wrote a journal article at JCM in 2013. And there's been follow-on work. This is actually sort of a cottage industry of refinements of the Calm theorem. But there's a key thing to understand. And we presented a sort of easy to digest version of this for sort of typical computer scientists, not specialists in distributed systems. And you can go read this. It was in CACM, the flagship magazine of the ACM last September. So I'll encourage you to have a look at this short 6-page paper if you want to learn more about the Calm theorem. To prove the Calm theorem, you do need formal definitions for its key components. What does consistency mean formally? What does monotonicity mean formally? And what really is coordination? And so those take some work. Intuitively, when we talk about consistency in this context, what we're talking about is that your program, your distributed services, when they work together, will guarantee a unique outcome regardless of the shenanigans in the network, regardless of whether messages get interleaved or reordered, regardless of whether there's delays or packets get dropped and so on. Okay, that's what we want. We want our cloud we want our cloud infrastructure, the computer we're running on, to behave reasonably, right? We want it to behave without having to worry about what every packet gets delivered. So that's our definition of consistency. That's a goodness. That's the goodness we want from our program. Monotonicity, the property we need from our program, is that the set of outcomes only grows during execution. If your program is monotonic, then you will be able to have a coordination-free, consistent version. So this definition of monotonicity is the more input you get to your program, the more outputs it generates. In particular, the program will never emit an output that it would later have to retract. So the program never learns something new that causes it to change its mind. Everything it ever outputs remains true forever, even as new inputs arrive. Programs of that sort are monotonic programs. And then finally, coordination. What is it and why should we avoid it? Coordination is the case where we have responses, network responses we're waiting for, even though we have all the data we need to progress. Right? So this is sort of the messages we do in a program that aren't about the data needed to compute. They're about some other stuff, right? And that's formally defined in Amelut's proofs, and it's really quite beautiful, actually, for those of you who have an interest in computing theory. I'd encourage you to look at that stuff. So hopefully that gives you a flavor of the kind of key components of the Calm theorem. And for more detail, I encourage you to read that CACM paper. So very nice. We had 5 minutes of core computer science in the talk, but who really cares, right? Why should you care about this academic stuff? You get this professor talking to you. Well, I actually have one foot in industry. I've done a couple startups, advised some large companies. I do think about what this stuff matters for. And in our research, what we've done is we've used our Calm thinking to build some crazy fast and essentially infinitely scalable systems to demonstrate that this stuff really matters. And the key here is just what James Hamilton told us, which is if you write programs without coordination, things will go well. In particular, you can get insane parallelism. You can just like pull all of the power out of all your cores all the time, and super smooth scalability. And I'll demonstrate this to you with some performance results in just a minute. So if you understand COM, you can build really, really sort of as fast as possible distributed programs. The other thing that's really interesting, and this was a lot of the work that we did in the research community over the decade, is you can design languages, particularly languages built on logic, where you can check for monotonicity very easily. It's like in the syntax of the language. And in fact, we have such a language, SQL. It's a logic language, and non-monotonic operations in SQL are super obvious. Like when you say not exists in SQL, not exists is syntax that says this is non-monotonic. It's true until you get a piece of information that makes it false, right? So it's something that starts true and ends up being false. So you might emit something early on thinking it's true and later on learn that it's false and change your mind. So not exists in SQL is like a classic example of syntactic non-monotonicity. And so when we designed the Bloom language, we took some lessons from SQL and we built a language that was very data-centric and very logic-centric. And we were able to do these monotonicity checks really easily. So we could bless programs and say, hey, you just wrote a program that will scale beautifully. Or we could say, hey, you just wrote a program and here on line 14, here's a place where you're using non-monotonicity. Are you sure you want to do that? And if you do want to do that, you're going to have to wrap it up in some Paxos or some two-phase commit or something like that, because otherwise it won't be consistent, right? So we were able to ensure that programs were correct, and we were also able to give developers the ability to find these distributed systems bottlenecks, the performance bottlenecks for distribution in their programs. And that was great. But, you know, we would get this criticism that like our language was weird, who would really write distributed programs in logic? I'd really rather write Java, right? Heard that a bunch in the 2010s. We hear Java a little bit less these days, but we still hear Python and other similar sequential programming languages, right? People, as a rule, have yet to really embrace logic outside of the SQL ecosystem. So we'll come back to this point. I think it was Bloom was a great academic exercise, but one of the reasons we didn't pursue it as a practical technology was exactly this. It's very hard to change programmer behavior. Last note about COM for those of you who are distributed systems aficionados. COM in many ways explains the CAP theorem and a lot of the debates about it, if you know about that. And so COM explains the times when you can sort of quote unquote cheat the CAP theorem and have all three C, A, and P, and the times when no, the CAP theorem holds C and A and P can't all be had together. And it's very much the case that inside the green bubble, you can have all three, and outside the green bubble is where the CAP theorem really is applying. Anyway, this is a conversation for another day, deeper conversation. We talk about it a bit in that CACM article, if you're curious. So as evidence of this, we built a key value store. It's called Anna. And our goal was to perform, as fast as the single node in-memory key value stores like Redis, but to scale like the biggest cloud systems like S3, okay? So we want super low latency, and we want to have super great scaling. And up in the right here is a bird. It's called Anna's hummingbird. It's actually the fastest animal for its weight on the planet. And its speed was actually measured here in Berkeley. So that seemed like a good mascot for our project. So Anna is built on a calm, sort of coordination-free notion of consistency, and it provides actually fairly rich consistency using techniques called lattices. And you can go read about Anna in the academic literature or find my blog posts on it. And it also offers auto-scaling. So it can scale up and down from one core to multiple data centers and back down. And it has multiple tiers. So you can have a memory tier of Anna over a disk tier of Anna, very much like we traditionally had a memory cache over a file system, right? And you have a single API for both, rather than wrestling with both Redis and S3. So it's got a lot of nice features in that respect. Now, Anna, in terms of performance, this is my favorite graph. It's small scale, but it illustrates the point. As you start adding cores to Anna, it just keeps scaling. So every little plus sign and X on this plot is another core being added to our Anna server with load being added. And you can see that throughput goes up beautifully linearly as we go through from core to core to core. And when we go from one server to two servers, so at 32 cores, the 33rd core is another machine. You see a very tiny blip as we see the network latency between the two machines, but things basically scale linearly. And this smooth scaling just keeps going, because every thread is working on its own without coordinating with the other threads. So this thing scales beautifully. Linear scaling in a distributed system is very hard. And then it's crazy fast under contention. So it's up to 700 times faster, excuse me, than what had been the previously fastest academic key value store in a multi-core setting, right? So on a single box, it can incredibly outperform other systems pardon me, particularly under contention. I mean, the place where this stuff gets hard is when you're getting reads and writes on the same keys. And that's the case where many of the traditional systems fall down, and Anna just does great. It's up to 10x faster in that setting than Cassandra in a geo-distributed deployment, and we showed that it's 350 times the performance of AWS DynamoDB for the same price. So for the same amount of hardware resources at Amazon, you could buy 350 units of our stuff and 1 unit of DynamoDB. And the key to this is that it's coordination free. It uses the calm design principle, which means there's no atomic instructions at all in the Anna key value store. There's no test and set. There's no locks ever. There's no waiting ever. There's no barriers. And you can see this in our performance results. When you look at request handling, under contention, Anna is spending 90% of its time or more just handling puts and gets and doing its job. Whereas Mastery, the next fastest system, under contention ends up spending 95% of its time trying to do atomic instructions. Test and set fail, test and set fail, test and set fail over and over. So under contention, Anna just keeps going because it's not coordinating. Traditional systems that do coordination basically spend all their time coordinating and can't move forward. So this is really just James Hamilton's lessons brought to a very fine grain and made very performant. The other thing, because of the calm theorem and our understanding of the math behind it, is that we're able to bring pretty rich data consistency to this key value store, richer than what you get out of most of the distributed stores out there, including things like DynamoDB. So we can give you causal consistency, read committed transactions, and so on under this model. So I told you a bit about the calm theorem. It's the bright line. Monotonicity is this bright line between what can and cannot be done coordination free. And I hopefully showed you that there's potential for really big payoffs from understanding this. So in the last few minutes of the talk, what I want to tell you about is what we're doing going forward in our research at Berkeley. And this is what we call PACT programming. So we're designing a new programming environment following on from our lessons on Bloom and our lessons building Anna. And the PACT programming model is a declaration of 4 independent facets. When you write a program, you should write down 4 separate things. First, what is the semantics of your program? Forgetting about distribution. What do you want your program to do for its inputs and its outputs? Basically, what should the docs be documenting, right? Independent of whether there's distributed systems or not. Secondly, tell us what your availability goals are for each one of your APIs. And that would be something like tolerate F independent failures of machines for this API. The third is to tell us what kind of consistency you want for your data. Okay, and so if you have application specific guarantees on different APIs, you can tell us what consistency you want. And then finally, as you'd expect, you want to target for optimization, some kind of SLA, which is usually a multi-objective optimization, trading off things like latency, throughput, and cost. But the goal is not to do this with a new programming language like we did with Bloom. The goal is instead to allow people to evolve their current programs into this environment. So this idea of evolutionizing this environment is part of the goal of the PACT programming model. So let me go through this quickly. Programmers are going to specify each facet in isolation. This allows them to very clearly say what their intent is for the program, separate out concerns of program semantics from distributed systems. And if you look at current distributed programs, they're a mishmash and an integrated tangle of program semantics and then logic for doing the messaging and the fault tolerance and all that for the rest of the stuff for A, C, and T. So we really want to separate those things out. And then each of these facets is going to have its own syntax and code generator in the compiler. And our compilation, we're going to lean heavily on program synthesis, which for those of you who know, is modern technology for doing code generation via search, using AI or using theorem provers, rather than the kind of rule-based compilers that have been built traditionally. So for program semantics, we want to have a declarative and logic-centric internal representation of the program. So in essence, we still like Bloom, but not for the programmer. Bloom should be for the compiler, because the compiler, once it gets that logic program, can do all the great things that Bloom could do. It can parallelize things, it can re-optimize them, it can figure out data lineage, and it can do the monotonicity analysis for the calm theorem. And so we believe in the future that we shouldn't have programmers deciding what order of instructions things should happen for a distributed system. Internally, the compiler should remove that overfitting that programmers like to put into programs and free the compiler up to do all these good optimizations. The key is we don't want the programmer to have to worry about this. And so we're going to take technology from my colleague Alvin Cheung here at Berkeley, which is called verified lifting, that takes traditional code and lifts it into a higher level domain-specific language, in particular a language like Bloom, that allows us to optimize it. So Alvin's work has done this already for things like converting old Fortran code that's in Adobe Photoshop into code into Halide that can be recompiled to GPUs. So you'll see mention when you boot up Photoshop of Halide, that's code that's being auto-translated from legacy code to Halide code via Alvin's verified lifting. So we're going to be doing this now for distributed systems code. So the hope is that we can take your sequential programs, or more particularly programs that have a little bit of hints, like programs over object relational mappers or programs that use actors or promises. These are common distributed systems interfaces for old-fashioned languages, and that we'll be able to lift them into a declarative internal representation that the compiler can then go to town on. So the verified lifting will take that imperative sequential code, generate declarative code, perhaps with some little kernels of imperative code as user-defined functions tucked inside it that we can invoke with serverless computing. For availability, it's pretty much simple. We want you to declare fault tolerance. So for each API, you should be able to say, I want to tolerate F failures. And then we should build a program and a deployment that gives you F+1 way redundancy efficiently. And then you should be able to also declare what kind of independence you can tolerate. So which correlations of failure will you ignore? So do you need to spread nodes across virtual machines or across data centers or even across availability zones to make sure that they don't fail at the same time? But this is really all you need to declare for us to do the availability part. And then for consistency, and this is in the theme of that Far Side cartoon with the dog, we're interested in consistency for your APIs, not consistency for storage. You shouldn't care about storage. You should care about your documented APIs. So you want a consistency guarantee for each API. And all that matters is what people see for the input-output pairs of that API. So you should tell us what you want to be the consistency guarantees for those input-output relationships. And then, probably don't have time today to talk about what types of guarantees there are, but in the literature, there's ones that are based on sort of transactional guarantees from databases, and there's other ones that are based on sort of property-based guarantees from programming languages, and we hope to support both. I will talk about that another day if you're curious. And then finally, the targets for optimization. This is, a classic challenge of the cloud that we've been working on as a community, which is to trade off cost and performance and to give people SLAs that we can optimize for. Our goal in this project to build a compiler for this whole PACT stack is to start this pretty simple. We can enrich it over time. But for cost, we're assuming we want to minimize client costs with pay-as-you-go, with maybe one or more pricing schemes we can imagine. And then performance, the basic challenge to start with we'll look at is hitting response latency goals. Some distribution of a median and a P99, and then figure that bandwidth can be handled by autoscaling. So this is kind of the stack we're building. Apologies, the fonts here are sort of didn't quite flow properly when I put it into projector mode, but we're looking to take at the top level many different ways of writing programs, use verified lifting in our system called hydraulic to translate them into our internal representation, which is hydrologic, which is this Bloom-like language where we have the PACT representation. And then the hydrolysis compiler will compile this down to actually a data flow program, which is, we believe, an excellent model for how to do distributed computing, even for low latency sort of service-based computing. And then there'll be a deployment layer. So this whole stack is being built out at Berkeley in the RISE lab where I'm a co-director. And our goal to start, is our modest goal is to deliver this with performance that's at least comparable to current functions as a service offerings like AWS Lambda. And you'll remember from early in the talk, I said those systems can be pretty slow. So we're actually setting the bar pretty low, but it's a bar that people are willing to use and pay for right now. So we feel like that's a fine place to start. And of course, we hope that the whole compiler stack will improve from there. So in the paper that we wrote about this at the CIDR conference this year, we talk about why we believe we can do this now. So we go over the literature and the results from the last decade on things like monotonic distributed programming, on things like verified lifting and program synthesis. There's been new results from some of my colleagues on mixed consistency and client-centric consistency, data flow and reactive programming, and why we believe that that's going to be a good runtime. And then the success of faceted languages like Halide that have been used in the verified lifting context to write really high performance code for GPUs. So the paper's here, and you can go fetch it and read about it. This is from the CIDR conference earlier this year. And for more information, we have a website for the Hydro project. The Bloom language is still up there. My students learn it as a way to kind of get versed in these ideas. And if you want to play with it, it's reasonably stable, so you can have a look at it. And then, of course, lots of stuff going on in the RISE lab, everything from distributed computing to security to machine learning. And I encourage you to have a look at our research. This is all joint work with my colleagues, Alvin Cheung and Natacha Crooks, who are professors at Berkeley, and our postdoc, Matthew Milano, who's an expert in this space. Okay, thanks. I think we have time for questions.
Thank you very much. That was amazing. Some mind-blowing stuff. While we wait a bit for questions to start rolling in, so can I have this like tomorrow? That'd be good. Like all of this?
Yes, you cannot have this tomorrow. Although actually we do have quite a bit of interest in like making this real. So one of the major venture capital firms in Silicon Valley is investing in letting us hire programmers and postdocs to go start building this out. And so unlike the Bloom era, where we were really just doing this and scratching our heads and having fun on whiteboards and building a little prototype, here we're going to get some force behind the arrow to try to really deliver this. But it's a more ambitious agenda, so I think we'll deliver pieces over time. And in the fullness of time, we'll see how things evolve. Research takes a little bit of a windy path. So this is absolutely a 5-year mission. This is not something we'll have tomorrow.
Yeah, absolutely. Thank you. Okay. We have a question here that says, can you summarize the core idea behind simple lattices used in NF for coordination-free consistency?
Let me see if I can. Yeah. Okay. So briefly put, a lattice is it's a mathematical construct. And for those of you who took your modern algebra class, I'm talking about joined semi-lattices, okay? But generally, the way you should think about them is an object class, all right? A lattice is an object class with one method called merge, okay? And that merge method takes 2 instances of the class and creates a new instance, all right? Or if you like, it takes 1 instance of the class and it merges the other into it. The merge function has to have 3 important properties. It has to be commutative, so the order you merge things in doesn't matter. It has to be idempotent. So if you merge the same thing in twice, it's the same as merging it in once. And it has to be associative, which if you remember from elementary school with algebra, it means that the parentheses don't matter. So for programmers, what that means is if you take a batch of objects and merge them together, it's the same as merging them in one at a time. It doesn't matter kind of how you batch things up. So if you're associative, commutative, and idempotent in your merge function, you have what's called a lattice. Knowing that you're associative, commutative, and idempotent means that you can get your messages on, say, 2 different replicas of this object in any order, in any batching, even with resends, and both of the replicas will agree on the outcome, okay? So that's the idea of lattices, and they're simple monotone data structures. They only get bigger. The more you merge in, the bigger they get. All right. Now, the lattices we use for consistency tend to be things like vector clocks. It turns out you can implement vector clocks as a lattice data structure. And vector clocks are kind of one of the key ways of implementing causal consistency, if you know what that is. So it turns out that we have earlier work from my group that shows exactly which consistency and isolation levels from the literature can be done coordination free. And then we have work on how to do coordination with lattices. We brought those together in Anna and delivered it into a system. So that's my 5-minute lecture on lattices. I encourage you to read the papers if you want to get it quick, with more patience than that.
Yeah, amazing. I'm trying to wrap my head around that, but yeah, it's probably not a 5-minute topic.
Yeah, it deserves a lecture.
Yeah. I'm not yet seeing any other questions. So if there's something that you want to hear Joe talk about, then feel free to drop them in the Q&A. I wonder, is there anything in particular that you wish people would or could start applying in the industry today from this bag of exciting stuff that you talked about?
Yeah, so I think already today, people who build distributed systems in professional contexts already understand that coordination is a problem. I mean, James Hamilton was talking about this a decade ago. If you learn nothing else from this talk, you should learn that you don't want to be using coordination mechanisms in your code. So you really want to avoid using transactions, and you really want to avoid using distributed agreement like Paxos or Raft. if you're in like a geo-replicated setting. Okay, in a data center these days, actually latencies and things are okay, but in a geo-replicated setting, that stuff is just way too slow. So if you take nothing else away, take that away, because that's a good rule of thumb, and beware of queuing effects if you do use that stuff. Super important to hide that stuff in the corner where other systems don't interact with it. Make it a background task. So that would be my most important lesson. And then my second lesson is that, you know, if you have something that's really mission critical and you don't know the answer to whether it can be done without coordination, that deserves some thought. You know, you shouldn't just say, oh, heck, it's going to have to be slow, or you shouldn't say, let's just turn off the consistency on this thing and hope it works. You should think pretty hard about it. And the place to go looking for more is this notion of monotonicity. And that's where you should send your research R&D team to go poking around.
Awesome. Those are some good tips, pointers. Thank you very much, and thank you for your talk and for answering these questions.